And of course, thanks to the organizers, Luigi, Jane, Emile, and everyone else for putting together this very exciting and, how to say, very well consistent workshop in terms of topics. It's very nice to find a community that is kind of meeting around a few topics that are of really shared and common interest. So today I present one of my kind of resource theoretic works, the works that we have done in my group. This was done with a PhD, at the time with a PhD student, Feynman, and with Renato Ren and Herman Manhong. All the results that I'm presenting are in one single paper, that is this one that you find cited here. So basically I'm presenting different aspects of things that we wrote in this work. Okay, so let me get started. Okay, of course, the clicker worked before, but it doesn't work now. Right. Oh. All right. Anyway, so what is the problem of that we analyzed? It's like, what is the cost, the thermodynamical cost of information processing, or more precisely, of accurate information processing? So we know that being accurate is extremely important in any information technology, in computing, classical and quantum, and communication, and whatever. It's also important in nature. The typical example here is the example of DNA replication in our bodies and in the living organisms. The estimates on how accurate is this natural process of DNA replication are actually very precise. So one of the estimated error rate is at most 1 basis per billion when the copying takes place in the kind of DNA replication. This is an estimate. There is no firm data, but kind of a recent accurate, relatively reliable estimate is this. So the question is, which kind of physical resources are needed to guarantee these high levels of accuracy? And yes, so this is the intuition here is that the resource here is the deviation from equilibrium. So there is the idea that when we store and process information, we store it into some patterns, in some way of encoding that deviates from thermal equilibrium. And the cost of accurate information processing is the cost of manipulating information away from equilibrium. And this intuition has been expressed in many ways in the literature. I think starting from Landauer's principle is probably the first articulate way to make this connection. And there was a lot of work by Charlie Bennett, on the thermodynamics of computation, even classical computation, that somehow was kind of at the origin even of the field of quantum computing. So what I do today is to take a resource theoretic approach and to see how far we can go and which conclusions can we get about quantifying the kind of non-equilibrium cost of information processing. The first topic that I will cover here is a review of work done by others, specifically by Feist and Renner in this PRX paper mostly. So this will be a review part now of the talk, to introduce the resource theoretic framework that we adopted, that was actually developed by them in this paper. So a few obvious definitions. So what does it mean equilibrium? Is, of course, the equilibrium state is the Gibbs state. So we start with the system with a Hamiltonian attached to it. So we define the Gibbs state. And then we consider the physical processes, the quantum channels that preserve equilibrium, that maintain the condition of thermal equilibrium. So if you have a process that transforms a system A into some other system B, which may be the same, may be different, we call the channel Gibbs preserving if it maps a Gibbs state of system A into the Gibbs state of system B. Now, this is a nice mathematical class of processes, and in terms of interpretation, we can interpret them as the largest set of channels that preserve the condition of thermal equilibrium. That's just a way to read this equation. So, making one step further, you could guess that they are the largest set of channels that, in principle, could be implemented at zero non-equilibrium cost. This is kind of it's sort of a bound, I would say. So physically, what we could do in the lab maybe it's not every Gibbs preserving channel. Maybe we would be restricted to thermal operations or other classes of operations. But in sense, at the level of principle, this is the biggest class that you could even think to realize at zero non-equilibrium cost. Now, what is the framework? So in this PRX paper in 2018, Feist and Renner defined a resource theory where you have an experimenter that is allowed to perform every Gibbs preserving channel free of cost. So these are the free operations, Gibbs preserving channels, and whatever is not Gibbs preserving would become a resource. So if you want to realize a non-Gibbs preserving channel, you have to mimic it by using Gibbs preserving channel and some resource states. So roughly the scheme is this. So you have a target non-Gibbs preserving channel C. You want to apply to a system A and get some output of system B. What you get is that you supplement the input with some resource states, some units of non-equilibrium, and this would be just qubits with a fully degenerate Hamiltonian in some fixed pure state. So you start with a bunch of qubits, kind of fresh ancillas in some fixed pure state. Then you apply a global Gibbs preserving channel to the input and to these resources, and eventually you try to mimic doing the right transformation that you want, and then you will have a kind of an amount of resources that is consumed in the process. So if you started with n units of non-equilibrium, with n pure fully degenerate qubits, you end up with n prime, and the difference between these two quantities would be the amount of the cost, the amount of resource that has been consumed in realizing this channel C. So the cost of this particular physical realization would be n prime minus n. Now, of course, for a given channel, you may have many physical realizations, so you would optimize over the choice of physical realization. So you try to find the minimum n prime minus n over all possible realizations that use this resource qubits and Gibbs preserving operation. In general, what you find is that the cost depends on what set of inputs you want to realize your channel on. You may want to realize the channel just on a restricted set of inputs. So you could have a subspace of the total Hilbert space where you really want to reproduce the action of C. So the cost will depend on the channel and on the subspace of inputs where you really want to implement this channel accurately. So in the paper by Feist and Renner, they provided an explicit entropic formula for what is the cost of the non-equilibrium cost of a given quantum channel. I will not give the formula here because we'll kind of build on it later, and we'll give you the formulas that actually pertain to our special case. But I would say the main result of the paper, besides the framework, is that there is this entropic expression of the cost of a channel. Okay, so this is the end of the review part of the talk. So now the question that we asked ourselves was, okay, we know what is the cost of a specific quantum channel. Now we want to ask a kind of a next question. What is the cost of accuracy in a given information processing task? Because the channel is the physical realization of information processing. You could define a task independently of what channel you're using, and then you may want to know what is the cost of accuracy itself, not of one specific channel. And this is really what our paper is about. So yes, saying again, quantum channels are typically the physical way to implement information processing. So, for example, you may want to copy data in a computer, or to factor a number, run some quantum algorithm, whatever. So this is the abstract information processing task, and physically you realize it with a given channel. So in many situations, the goal is actually to have high accuracy in the information processing task, and we can ask what is the cost for that. And so what we give here is some answer to this question. So now let's get a bit more formal. So what is an information processing task in an abstract sense? Well, classically, the easy example is computing a function. So you get an input x, and you want to produce f of x, to output f of x. The quantum analog of this, the naive quantum analog, is that you have a possible set of input states, rho x, this could be mixed or pure states. You have a set of target states, rho x prime, and you would like to implement a state transformation that given rho x produces in output rho x prime. So this is kind of the information processing task. Examples, for example, erasure means is the task where you want to map every input density matrix to a fixed state, let's say to the ground state. Unitary evolution is unitary evolution. You want to map unitarily the density matrix. So these are tasks that we can implement in principle with absolute perfect accuracy. And there are also some tasks that you can define, like cloning, like perfect quantum cloning, that are well defined as information processing tasks in abstract, and in practice they cannot be realized in the laboratory because they are forbidden by the laws of quantum mechanics. So here you see really the difference between an information processing task as a sort of abstract input-output relation and what you can really physically realize. So when we have quantum cloning, we can only have approximate realization of quantum cloning in the laboratory because of the rules of quantum mechanics. Another example is the complex conjugation of the density matrix or the wave function. This is another example of an information processing task that you can define easily in an abstract sense, but you cannot in principle implement exactly on a quantum system. All right, when we talk about physical implementation, the physical implementation of an abstract information processing task is a quantum channel that will transform the input state rho x in some output state C of rho x, which may not be the state you wanted, and maybe just some approximation of the state you wanted. So the way to test how good is this physical implementation in an operational way is to make some measurements on the output and to see what is the result of this measurement. So we can imagine that we have a set of observables, OX, which can be completely arbitrary, and then the testing, we do a measurement of this observable, and the expectation value of this observable of the output would be a measure of success, of how good is our implementation. So the mother of all examples here is the fidelity, the easiest example. If you have a pure state transformation, if your goal is to produce some pure state output, then an easy example of a score observable would be this, just the projector on the state. It gives you the fidelity. So I will actually call the accuracy F because our main example, the example you have in mind, is actually the fidelity. So right, so after you have chosen your figure of merit, you have chosen your set of observables, so the accuracy would be the worst case score that you get, minimized over all possible inputs where you may want to implement this information processing task. So this minimum over all possible X would be the kind of the measure of success, the measure of accuracy that we use. More generally, you could define the task in a even more abstract way. Instead of saying what are the target output states, what are the input states, you could just consider some performance operator, omega x, and the trace of this performance operator with the Choi operator of your channel would give you some quantity that you can use as a measure of performance. And the example I gave you here is just a special case of this, where omega x is a product of an input state and an output observable. But in general, you can choose an arbitrary measure of performance to quantify the quality of this implementation. Okay, so now we can say, what is the cost of accuracy? So the cost of accuracy is the minimum amount of resources that we have to pay in order to achieve a level of accuracy F in a given task. So this is the minimum over all possible channels, over all possible physical implementation of the information processing task, the minimum of the cost of that implementation under the condition that the accuracy of the implementation is larger than the fixed value, the desired value F. So this becomes a function of the accuracy itself and of the task itself, and not a function of a specific channel. And so this is the quantity that we will care about in the remaining part of the talk, and this was the quantity our work is about. Okay, so the first result is that we can find a concrete SDP formulation of this cost of accuracy in the case where the input states stay in a subspace that is invariant under time evolution driven by the original Hamiltonian. So if the projector on the input subspace commutes with the Hamiltonian of the system, then we have this expression that contains an SDP inside it. So the details here are not important. You don't need to parse this equation to understand the rest. But it's good to know that we have an explicit expression, at least of this kind, with this nested optimization. Sometimes this can be solved, I mean, analytically by hand. Sometimes, most of the time, it cannot. So actually, the result that I consider the main result is a relaxation of this exact value that gives us a bound, basically coming from choosing this one of the optimization variable xa to be 0. If you choose that, you get the cost can be lower bounded by the contribution of two terms. One is just the logarithm of the accuracy you want, or the logarithm of the fidelity. So this is where the accuracy goes. And this is another entropic quantity that you get here that depends on the task itself, only on the task, and not on any specific channel. So this is given by a conditional mean entropy. And it's not really the mean entropy of a state, but is the entropy of this strange operator that you get here, where you have the performance operator defining what is the task, what is the figure of merit, and you have these Gibbs square roots of Gibbs states around to somehow to match, I don't know how to distort the original performance operator. So this is actually the equation that gives most insights into the problem, and the one I will talk most about now. So this term that depends only on the task is a term that we call the reverse entropy, and I will use the letter kappa for it in the next. So the first thing is to ask, how do we interpret this strange quantity, this strange reverse entropy that appears here? The idea is that we can introduce a sort of notion of time reversal of information processing tasks, and you'll see that this reverse entropy is related to this notion of time reversal. So if you have just a task where you go from a system to itself and there is no energy, so the energy is completely degenerate, the idea of time reversal is simply to exchange the roles of the input state rho x and of the output observable. So you pretend that the observable is a sort of like an input, and you treat the state rho x as a sort of observable in the output, and this defines a sort of time reversed task. More generally, if you have a task that is defined by some performance operator omega x, we can define a new performance operator reverse of omega x through this equation. So this equation tells you that basically the performance of the original performance operator on a quantum operation of a trace non-increasing completely positive map that is a sub-Gibbs preserving should be equal to the trace of the new performance of the operator, the reversed one, with the time reversal of the quantum operation, of the original quantum operation. So what is time reversal is basically the PETS recovery map, except that the original PETS recovery map was defined for channels that have that transform a state into another. Here we apply it for quantum operations, but the expression is the same of PETS here. Okay, so good. We have this notion of a time reversal of a task, and it turns out that you can express the reverse entropy as the minus logarithm of the fidelity of the accuracy in the reverse task. So this kind of the performance measure in the reverse task determines this contribution that we call the reverse entropy. So basically here we have the maximum accuracy that we can achieve in the reverse task, and this F max, the reversed, would be the quantity that appears in the bound. So in other words, you can rewrite the bound as the cost of accuracy F is the logarithm of the ratio between the accuracy you desire and the maximum accuracy allowed by quantum mechanics in the reverse task. So this lends itself to a kind of nice slogan, a kind of nice physical interpretation that the hardest is the reverse task, the higher will be the cost. So the smaller is this accuracy, the maximum accuracy of reverse task, the larger will be the cost, which sounds pretty much consistent with what we knew before with Landauer and other cases, that the irreversibility somehow is what controls the cost. Although there is an interesting caveat, so there are two examples, a very classical one and a very non-classical one. So if you just want to compute a function, compute a classical function from x to f of x, the cost is really the max distance between the state that you get when you apply the ideal function to the Gibbs state and the Gibbs state on the output state of the output system. So this is really how much you deviate, how much the average output state deviates from the thermal equilibrium state. And this is what pretty much I think everybody who has read a little bit about these topics would expect here. But this is a very classical type of task. Like on the opposite of the end of the spectrum, if you consider the complex conjugation of pure states, where you try to map raw into the density matrix with complex conjugate entries, you get that this reverse entropy, in the case of fully degenerate systems, is log of the dimension plus 1 divided by 2. So there is this constant, and this is, of course, non-zero when the dimension is larger than 1, so always, there is always non-zero, despite the fact that this complex conjugation maps the Gibbs state into itself. So there is no deviation of the ideal state from thermal equilibrium, but you do have a non-trivial source of irreversibility, because basically the complex conjugation is forbidden by the laws of quantum mechanics. So this type of irreversibility even contributes to the thermodynamical cost. It's not only the logical irreversibility, but it's also the physical irreversibility due to the constraint imposed by quantum mechanics. Okay, so our bound can actually be achieved in many situations. So this can become an equality, for example, for all deterministic computations of function, for every quantum extensions of this deterministic computation, and for there are other cases like universal cloning and complex conjugation. Let me give you a couple of examples. One is erasure. When you want to turn every possible input state into the ground state, you take the fidelity as the figure of merit, and you get from our result that you have the exact cost of approximate erasure that's given by the free energy difference between the Gibbs state and the ground state. So this would be the reverse entropy contribution plus log of the fidelity. So this is exactly the value of the non-equilibrium cost, and in this case it coincides actually with the work cost defined by thermal operations. So in this case it's kind of the easiest and simplest case where we can compute the non-equilibrium cost, and the non-equilibrium cost coincides with the work cost. In general, this would be a lower bound. Another example is the DNA example, the example of classical cloning. If you have a bunch of identical copies of a classical state and you want to produce more copies, again, with the fidelity as a figure of merit, you find out that the cost has this expression where you have the number of extra copies you are producing times the maximum free energy that you might have to generate going from the Gibbs state to a pure state, to pure classical state. So the free energy of the maximum, the state with maximum energy, and this again gives you exactly the non-equilibrium cost. We don't know in this case whether this coincides with the work cost, but at least the non-equilibrium cost is well defined here. Now it's interesting that if you look into quantum cloning, so transforming pure quantum states into more copies of pure quantum states, using the global fidelity as the figure of merit, you find out that the cost is exactly the same of classical cloning. So despite the fact that we are approximately copying all possible quantum state, the trade-off between non-equilibrium and cost is exactly the same. So the difference between classical and quantum cloning is just that, is that quantum cloning saturates before reaching fidelity 1, whereas classical cloning can go all the way, but when they are both possible, for the values of the fidelities where both are possible, the trade-off curve is exactly the same. So the thermodynamical cost is the same. All right, so now I would like to use the last 5 minutes to answer a question that was natural to me, and I don't know if it's natural to you now. So I was finding this result about cloning a bit striking to me. I was expecting that in quantum cloning there should be some thermodynamical advantage in processing the information in a genuinely quantum way, whereas it seemed that as long as I care only about accuracy versus non-equilibrium cost, classical and quantum are exactly the same. So I was saying, like, no, it shouldn't be like this. There is some intuition that a genuine way to process quantum information, like as opposed to doing measurement, should give you an advantage. And this intuition is kind of vindicated if you look at how classical cloning works and how quantum cloning works. So the way you clone in the classical world is by measuring first and then making copies of what is based on the information you got. So classical cloning is basically a measure and prepare type of channel. And measure and prepare is a special case of a larger class of channels called entanglement binding. So channels that acting locally can map every entangled state into a PPT state. So they degrade the quality of entanglement from free entanglement to PPT. as defined in this work by the Horodetskis. So you can ask, what is the cost if you constrain yourself to use an entanglement binding channel instead of using any possible quantum channel? And it turns out that there is an expression for the cost of entanglement binding channels that has, instead of just having the reverse entropy, it has the maximum between the reverse entropy of the task you started from and the reverse entropy of the transpose of that task. So basically this PPT property becomes the fact that you have an alternative task where you have the transpose and the same channel can do, or a related channel can do equally well. So you can consider the transpose task where you transpose the output and you have a bound where the cost is controlled by this maximum. Now, if you do this in the case of cloning, you find that the transpose task of cloning is just the cloning and the transposing the output. And for this one, there is a strictly larger cost when the system has a non-trivial energy spectrum. So if your system is not fully degenerate, there will be an extra contribution in the reverse entropy and therefore in the cost that comes exactly from this entanglement binding requirement. So we have a higher cost for all the cloning processes that are constrained to be entanglement binding. And therefore, if you look at it in the other way, it means that there is a thermodynamical advantage of using genuine non-entanglement binding processes in doing this task of cloning. All right, so I'm done. I will just leave you with a few take-home messages. So the first is about the framework. So we define this notion of the non-equilibrium cost of accuracy as the minimum number of pure state clean qubits that are consumed by the best implementation possible if you try to achieve a desired level of accuracy in a task that you want to achieve. And I would say the main result is a bound on the non-equilibrium cost, and is a bound that in many interesting cases is tight and can be achieved exactly. Not always, but in many interesting cases is a tight bound. And also, even when it cannot be achieved, is a nice bound because it separates the two contributions, the one of the task and the one of the accuracy. So this, I would say, is the main result. And then we have used this bound to get physical insights into how the thermodynamics of accurate information processing works, and in particular to see these advantages of genuine information processing when you try to process information, like to do quantum cloning and other genuinely quantum tasks. That's it. So with this, thank you for your attention. I'm happy to answer any question you have.
Right. Any questions? Here first. Yeah, thanks a lot for the talk. One thing I had the feeling is at the heart of the result, there is the maps you look at, which you consider that they are thermodynamically for free, or whichever resource you consider. And these are the Gibbs preserving maps, if I understood that correctly.
Very correct.
Is there a practical example that you know to somehow motivate or explain in which situation such maps would actually be for free when done in practice?
It's a good question, and the first quick answer is no. I am not really, I cannot provide you an example where these maps are physically relevant, except examples in which we can achieve our bounds with other sets of maps. So these are examples we have. But for me, it's more like a slightly different way to look at the terms of the problem. When I use the resource theoretic framework here, and also in other cases, what I call free is not necessarily something that is easy to do in the lab, but means something that I want to kind of factor out from the equations. Now I want to say, let's say that this part is the kind of the one I don't care about. And then let's see what would be the cost. So in a sense, I would say this is more like a bound, a lower bound on the cost for more physically meaningful set of operations, like, for example, the catalytic thermal operations or thermal operations. So these are the ones that, honestly, I agree that physically would be more meaningful. On the other hand, this constraint of Gibbs preservation mathematically is very simple because it defines a spectrahedron. So it has all the nicest mathematical property, and this is why people often use this So this is the analog of using unital maps instead of noisy operations or random unitaries when you talk about purity. It's convenient and it gives you a bound because this is in principle the largest possible set.
Yeah, I mean, I have many more questions, but
maybe
I'll
we can
try
chat
to
about
ask
that
later.
later. Sure,
Thanks a
sure,
lot.
sure. Thank you.
Yeah, okay, kind of. Yeah, thanks for the very nice results.
Thanks.
Great talk. I had a question, and this reminds me, like this picture reminds me of fluctuation relations, where you have a forward process, you have a reverse process, and
Yes.
relate properties of one to the other. Is there a connection beyond the analysis?
There is. That's another excellent point. So the way the time reverse of the task that I defined here, actually defined through this relation with the time reversal of operations, which this is the only result you wouldn't find in the paper. I just added it as a kind of a further way of presenting things that came up after we published the paper. So that makes the connection, because there you really have the time reversal of the operation, the physical operation. And this time reversal of operations appeared in the work by Crookes. I mean, basically the use of the PETS map, which Crook didn't know was the PETS map, but the use of that distortion with the Gibbs state and Gibbs state to the -1/2. So that appeared in the work by Crookes that was done to study fluctuation dissipation relations. So there is a very solid and strong connection. Now we haven't explored much what insights we could gain if we were to take what the work we have done and bring it into that context, and vice versa. So this is a good thing to do, to look into more like what is the cross-fertilization, what is the kind of benefits that we can get by comparing the results we have here and with what people were doing in fluctuation dissipation theory, but we haven't done it yet. But the connection is definitely there, and it was in that equation, basically. Thanks.
We have time for one more short question.
Very simple question. What is the non-equilibrium cost of the identity?
Well, if you do it exactly, it's a 0. And if you do it approximately, it could be slight. I mean, if you use the fidelity of the measure, it could be slightly less than 0, because it means that you can steal a little bit of an equilibrium by making a suboptimal identity that adds a bit of thermal state. Let's say with probability, like a kind of a simple way would be to say, with probability P, I really realize the identity. Probability 1 minus P, I prepare the Gibbs state. Sorry, mistake. So this is true, it's not true. This is true if you restrict the identity to a subspace. If you want to realize the identity on a smaller subspace, you can gain an equilibrium. Otherwise, it's just 0. So the cost remains 0. And actually, this is a good point, because this is something that I didn't really highlight in the talk. So the bound we have holds not for every value of the accuracy, but for every value in the sort of meaningful interval between the maximum. I mean, if you go above fidelity 1, there is no point in increasing the cost, in putting more resources if you already have fidelity 1. And there is also a lower bound that for the identity is also 1. That is to say, like, if I already spend the minimum possible cost I could possibly spend by acting on this subspace of input state, what fidelity do I get? And for the identity, that's 1. So you can get negative cost only if the input is restricted to a smaller subspace. So now you can draw resources from the prior information that the input was constrained into a smaller dimensional, in a lower dimensional subspace. Thanks.
I think we have to go on to the next talk, and let's thank Giulio again.